Well, guys, in our previous sessions, we did went through just a minute. We did went through the concepts of channels, wherein we modeled channel, where we modeled channel mathematically, and we did got to know about a lot of things related to the channel, and we did also went through different sorts of channel. And along with that, we did also solve a lot of problems on that, wherein we did try to find various parameters, and mainly we focused on to capacity of that channel. So this was about our previous module. But all of this, but along with all of this, we did also got to know that this channel that which we have, it has some additional uninvited guest called as noise. And this noise is something that which can corrupt our message signals. So whatever message is being transmitted onto the channel, so if I assume this to be our channel, so because of this additive noise, whatever we transmit, whatever input messages that we transmit might get corrupted, and whatever output that which we get over here might not be exactly same to that of whatever that which was transmitted. So here in our next module, in our next module, that is module number 4, here we will go through a lot of measures by which we can corrupt the effect of this noise, or if at all if there is any error happening over this channel. So what we'll do is we'll employ lot of methods called as error control coding. By this error control coding, even if there is any error happening over here, even if there is any error happening over this transmission, but still we'll be able to identify, as well as, so the very first one is to identify the error, or it's also called as detection, error detection. And the next part is error correction, because just detection will not work. After detecting the error, we should also correct it. So by employing various error control coding techniques, we can detect error as well as we can correct those errors happening because of this channel noise. So here, let me first take you through the block diagram, wherein we'll get to know what blocks play essential role in error control coding. So again, I'll be drawing the basic communication block diagram with respect to information theory. So here The very first block that which plays an important role is our channel encoder. So by now we know that prior to this channel encoder, there was something like source encoder that which did some source encoding. So source encoding is nothing but wherein, so if I consider this source encoder block, so source encoder block is something that which mapped symbols to code words. So source encoder is something that which mapped symbols to code words. So this was actually being done by source encoder, and now these code words are binary in nature. These are binary in nature. So by now we know that in order to map this from symbols to code words, we did also went through a lot of techniques, right? So what all techniques did we went through? We did went through Shannon's encoding algorithm, Shannon-Fano algorithm. We did also went through this Huffman coding as high as possible, as well as low as possible. And along with that, we did also went through something called as prefix code. So all these are what? These are different algorithms that which can be used to map symbols to code words. But the thing is, I cannot directly transmit these code words. I cannot directly send these code words to the modulator. I can do that, but the thing is, this leads to lot of errors. This leads to a lot of errors. So right after modulator, we have this channel. So before I transmit these code words to the modulator section, what we'll do is we'll introduce one more new block. We'll introduce one more new block called as channel encoder. So by introducing this channel encoder in between source encoder and the modulator, so this channel encoder works on this code words in such a way that it makes these code words suitable to go through this channel. So that is how this channel encoder works. So it works in a manner such that even if there is any error happening, we will be able to detect, we will be able to detect as well as correct those errors back at our receiver end. So here, back in our receiver section, what all blocks do we have? So right after this, we have demodulator block, and right after demodulator block, we have one more unit that works in the exact opposite manner to that of channel encoder, and we call that block as channel decoder. And next we have this source decoder. So now we'll see how exactly what all formats are being transmitted, or how exactly this channel encoder plays an crucial role here. So this module 4 is all about channel encoder as well as channel decoder. So here for timing, will not be considering the source encoder because it's already been discussed, as well as source decoder. Will not discuss much. Okay. So right now we are, well, this should be in the other direction. Okay. Right now what we'll do is we'll consider this channel encoder, and to this channel encoder we'll think of some input message, and here we'll think of these input messages in terms of blocks, or in general it is represented as b subscript k, and this block b subscript k is being transmitted into this channel encoder at a bit rate of rb bits per second. So the bit rate over where bk is being transmitted into the channel encoder is rb. This is small r subscript b bits per second, and we call this message as a block. By now we already know that it is called as a block. Now here any block that I consider is associated with its own size. So here we have written the subscript k, and over here k represents the size of the block. So what is k over here? K is the size of message block. So I can think of this message to be a block containing k number of bits. So when I transmit these k bits over this channel encoder, so what it does is it adds additional message bits onto it. Additional, I cannot call it as message bits, we can call it as check bits. It will add additional check bits. So it so happens that what channel encoder does is, to this k bits, to this k message block, this is same as that of this, onto this k message bits, it adds additional bits called as check bits, and these check bits are of what length? It is of length n minus k. So the blue colored block that I'm trying to write is the check bits block. And how many such check bits are getting added up? It is of size n minus k. Such that if I try to evaluate the total size of this block, if I try to evaluate the total size of this channel encoder output block, it will be equal to that of n, because it is evident that if I try to add n minus k plus k, if I try to do this, where n minus k is the block size of check bits, so this is the size of the check bits, and k is the size of this message block. So if I try to add these two, so these two gets cancelled out. These two gets cancelled out, and I'll be left out with n. So over here, this channel encoder will give us a block that which is of size n bits. So the input to this channel encoder is of k bits, and the output from this channel encoder is of n bits. So here we can call it as n bit code word. So here this is called as k bit code word. This is our k bit code word. that which will get from source encoder block, and output of this channel encoder is called as n bit code word. Now this bit rate, so obviously the bit rate has to change because the k bit code word was getting into this channel encoder at a bit rate of rb bits per second. Now the bit rate changes because we are trying to add additional check bits. So the modified bit rate will be r subscript c, will be denoted by r subscript c, that which can be related to this bit rate rb as equal to, so this rc is equal to rb, but it is scaled by a factor of n by k, where n is the size of the output of the channel encoder, whereas k is the number of bits that which is input to the channel encoder. So this is rc is equal to rb dot n by k. So this is the rate at which the channel encoder will be outputting code words or will be transmitting it onto the modulator section. So this is bits per second. Now this block of n bits will get modulated and will transmit via this channel and will be received over this receiver stage. Now here whatever n bit, so right after demodulation, we'll get n bit code word. Again we'll get n bit code word, and this n bit code word need not be exactly similar to that of whatever we have transmitted. So thereby what we'll do is we'll indicate it by dk, we'll indicate it by dk cap, because this is an estimation, this is not the exact copy, this is not the exact copy, this is an estimation. So thereby it is being represented as dk cap, whereas here I can call it as just dk. Here I can call it as dk here, but here I'll call it as dk cap because I am trying to estimate whatever that which has been received, and it need not match with that of dk that which we had transmitted. And and when we make this dk cap to go through this channel decoder, we'll get our bk, and this is again an estimation, and again it need not match this dk. So again over here the bit rate will be rb, and whereas here input to this channel decoder bit rate will be equal to rc. So this is how our channel encoder functions. Now before I continue, am I audible or is there any problem being faced? You can let me know if at all if you are facing any problem. So whatever content that I'm trying to share, is it visible? I want you guys to put it in the chat section. Madhu, it's not visible. Whatever I was writing, was it screen is not visible? I'm not talking right now. Before this, whatever I was trying to share, was that visible or not? Right now, I have ended the presentation. And I'm asking you whether the previously whatever I was writing was that visible or not. Ah, okay, good. Okay, let's get back. So here we'll define a quantity. Here we'll define a quantity called as probability of error. So considering our previous block, considering our previous block, here we'll define a quantity called as probability of error. We'll define a quantity something called as probability of error such that this probability of error can be mathematically be represented as probability of error. This is capital P subscript E. So this is equal to probability that this estimated bk, this estimated bk is the output of channel decoder. So this is the value that I'm trying to consider. So here I'm trying to consider this value. This is bk cap here represents estimated quantity, estimation. So cap over here always represents what? Estimation. So whether this bk cap is equal to this bk. Thereby, your probability of error is equal to whether bk estimated is equal to or basically not equal to bk. So if these two matches, then there won't be any error. But if these two are not matching, if this bk is not similar to that of this bk cap, then there will be some kind of error. So this probability of error is given as information block bk cap differs from that of transmitted block bk. So this is probability of error. And our error control coding, our error control coding always aims to reduce this probability of error as less as possible. So we are supposed to employ error controlling techniques as that this probability of error becomes lower than some desired value. So this is our main intention. Now let's try to discuss different methods of controlling errors. Methods of controlling errors. So mainly we have two methods, and the very first method is called as forward acting error correction. And this forward acting error correction is abbreviated as FAEC. And the other method is error detection. So in the very first method, errors are detected and corrected by proper coding techniques. So here we'll employ some coding techniques so as to detect as well as correct errors. So coding is used to detect as well as correct errors. So this correction is being done at the receiver end itself. So mainly both detection as well as correction happens at the receiver end. So here we are supposed to mainly concentrate on this correction term. So basically at the receiver end in FAEC, correction is also being done at what end? This receiver end. So back at this receiver end, correction is being done. But whereas in the other method, that is error detection, so decoder checks the input sequence. When it detects any error, it rejects that part of the sequence and request transmitter for retransmission. So here in the second method, all it can do is only detection. We'll employ again coding over here. We again will employ this coding wherein it does only the detection part at the receiver end, and there is no correction. No correction is being done over here. No correction is involved. So what the receiver does is it again sends a message to the transmitter. What it does is if there is any error will be discarded. Error bits are discarded. Here we'll not discard these error bits. Instead of discarding, we'll correct those error bits. But whereas here in the other method, we'll discard these error bits and we'll ask the transmitter to retransmit the message bits. So this is the main difference between forward acting error correction and error detection method. Now the thing is, this FAEC is, if I compare this FA, that is forward acting error correction, with that of error detection, this is much more faster. This is much more faster. But the only drawback of this FAEC is that in the approach to correct these errors happening, there might be some probability of error. So in this case, probability of error is high. Even though we are trying to correct and detect the errors as well as correct the errors. So in this case, probability of error is usually high because back in the correction technique, we might, so in many a times it might not work correctly. So in such kind of cases, the probability of error, that makes probability of error to be a little bit slightly higher than that of the error detection method. But whereas this thing is slower, this is slower, but probability of error is lesser compared to that of forward error, forward acting error correction method. So why is this slower? Because we are trying to detect the errors. What we'll do first, do detection. Okay. Right after detection, are we trying to correct those errors? No, we are not trying to correct those errors, but instead of correcting, we are trying to discard it. So this discarding of bits takes time, and after that, what we'll do? We'll ask the transmitter. We are trying to ask the transmitter to retransmit the message bits, correct the message bits. So thereby, this is slower in nature, but probability of error, it's lesser compared to that of forward acting error correction method. So these are the two methods that which we have. Now let's try to discuss the types of errors. So back in the type of errors, we are having two kinds. One is random error. The next one is burst error. So here, in the very first one, as the name itself indicates, it's an random error. So here, transmission errors that occur due to the presence of wide Gaussian noise are referred to as random errors. So this random error is mainly due to white Gaussian noise. So basically, errors that which happen due to wide Gaussian noise are referred to as random errors. And the source for this source that which causes these random errors to occur, or this wide Gaussian noise to occur, is thermal and short noise. Sources for these kinds of noises are thermal and short noise in the transmitting and receiving equipment. Because any system includes, so here this, because it involves all the modulator and all, right? This modulator, by now we know that it includes lot of electronic equipments in it. And when these electronic equipments operate on some power, they usually get heated up. So thereby, this will in turn lead to this thermal and short noise, that which causes this wide Gaussian noise to take place. And because of this wide Gaussian noise, the bits might change. The whatever bits that which we are trying to communicate or we are trying to pass to the receiver end, there it might lead to an error. And this error is random in nature. We cannot predict it. And thereby it's called as random error. The other error kind is burst error. As the name itself indicates, it's burst. Burst is something that which happens in a large scale. So these are the errors that which are generated by impulsive noise in the channel. Impulsive noise in the channel. And let's see what causes this impulsive noise. So the source for this impulsive noise, or in turn that which causes burst error, is lightning, as well as switching transients, and along with that some man-made noise. So these are all the sources for this impulsive noise. Now it has got the name burst error because it might affect more than one symbol. So this affects, so whereas random error affects only one symbol, but whereas here this will affect more than one symbol. Here it affects only one symbol. whereas this burst errors occur more than one symbol. So there are two sorts of errors. One is random error and the other one is burst error. In a similar way, let's try to go through the types of codes that which we'll be discussing here. Under types of codes, the very first type of codes that which we'll be going through is block codes. So in these block codes, it consists of n number of bits in one block, or it's also called as code word. And this code word consists of k message bits and n minus k redundant bits, such that block codes are called as n minus k block codes. So here this block codes are composed of, so this block codes is nothing but this this entire block. This entire block can be called as a block code. So its entire size is n bits. So it consists of n number of bits, and this n number of bits in turn contains. So how many message bits was it containing? It was containing k message bits. So this is our actual message. K number of message bits, and along with that k number of message bit, it also had some check bits of size n minus k. So in block code, the overall size is n bits, wherein out of which k are message bits and n minus k are check bits. So these check bits are also called as redundant bits. So these are called as redundant bits because they are like extra bits. Redundant bits or extra bits that which we are trying to forcefully bring in. Now you might be wondering, so now you have to ask one question. I don't know how many of you are getting this question or not. So you have to get this question. What question? Let's see. So back in source encoder, what we were trying to do here, back in our source encoder. Back in our source encoder, we were trying to map symbols to code words. And what was our aim? Our aim was to convert these symbols to code words that which had very less number of bits. Less number of bits. That is, any symbol that which was associated with high probability of occurrence. Higher the probability of occurrence, lesser number of bits. Less number of bits assigned. This was our ultimate aim. So this is what we were trying to do. And right after this, so here we were mainly concentrating on what? We were mainly concentrating on lesser number of bits. So source encoder, back in source encoder, we were trying to eliminate redundant information. We were trying to eliminate something that which was redundant. But in the very next stage, what we are trying to do? We are trying to bring in some redundant bits. Here, source encoder deals with remove redundancy. It deals with remove redundancy. or some redundant bits, whereas in channel decoder, whereas in channel encoder, channel encoder, we are trying to bring in some redundancy. We are trying to bring in or add redundancy. Now, the thing is, in the very first part, we are trying to remove this redundancy, and whereas in the very next part, we are trying to add in some redundancy, or we are trying to bring in some extra information. Now, now there is a difference between these two. There is a difference between these two things, and that difference is that, so in the very first source encoder stage, this redundancy, we have no control over this, no control over this redundancy. So we being users, we have no control over this redundancy. But whatever redundancy that which we are adding in the next stage, in the very next stage, that is channel encoder. So this is where I am trying to introduce it, and I know all in and out of that redundancy. So I have full control. Full control over this next redundancy that we are trying to add, and we are trying to bring in all these redundant bits or the check bits by using some algorithm. Because it's all algorithm based, I'll be having full control over it. And this adding redundancy is very much essential, because in order to detect and correct error, in order to detect and correct error, this is very much essential. So where were we were discussing about these block codes. So block codes are something that which has a block of n bit, that which contained k number of message bits, and along with k number of message bits, it had n minus k check bits, and this we call as block codes. And along with block codes, we have one more code called as convolutional codes. We call it as convolution codes. So in this code, the check bits are continuously interleaved with the information bits. The check bits verify the information bits not only in the block immediately preceding them, but in other blocks as well. So this is about convolution codes. So wherein check bits are continuously interleaved. So we'll be trying to insert these check bits. Again, check bits will be introduced with the information bits, but the check bits verify the information bits not only in the block immediately preceding them, but in other blocks as well. So there is a way in which these check bits are getting inserted. So that makes this convolution code differs from that of block codes. So block code size is always fixed. It's of n number of bits. Whereas here in convolution codes, so there is no block size. No block size. But still we'll be introducing these check bits onto these convolution codes. So having got to know about the types of codes, now let's try to go through this block codes. let's take up these block codes and we'll try to go through it in detail. So our next topic of discussion is block codes, and here we will specifically call it as linear block codes. We will specifically call it as linear block codes, and we have a reason for that. And before we get to know that reason, let's try to go through its block diagram representation. So we'll see why it is called as linear and all. We'll see that. So for this, in order to get to know about linear block codes, let's first draw channel encoder diagram, because your channel encoder is the block that which is introducing extra bits. This is the block wherein we'll be adding redundant bits. Sorry, what did I just do? This is not decoder. This is channel encoder. So back in the channel encoder, what we'll do is, so we'll have message block. And this message block will be of k bits length. Its length is equal to k bits. And this k bit messages, we are getting it from source encoder. From source encoder, we'll be getting this as our output. And now in the channel encoder stage, we'll be adding redundant bits. We'll add redundancy. We'll be adding redundancy such that, or to this k bits, to this k bits, we will add check bits. Excuse me, we'll add check bits. And this check bit is of size n minus k. And this message is of k bits. On a whole, the entire length is k plus n minus k, such that kk gets cancelled out and we'll be left out with n bits. So this is called as linear because the size is fixed. Because here the size is fixed and the number of bits that which are getting added is also fixed. So this channel encoder block always adds n minus k bits to it, such that if my message bit is equal to 4 bits, let's say 4 bits, and here let's say ultimately I am getting something like 7 bits. So here k is equal to 4 bits. Input to this channel encoder that I'm trying to pass in is 4 bits, and output from this channel encoder is 7 bits. So how many check bits am I trying to add? It's equal to 7 minus 4. 7 minus 4 is 3 bits. So this number is always fixed over here. So here, let's say I'm having continuous strings of ones and zeros. So before I form this block, what I'll be doing? So now I'll be doing this grouping. So grouping of how many bits am I supposed to do? I'm supposed to group 4 bits. 4 bits over here, next 4 bits. So I'm supposed to form this sort of grouping. And right after grouping, I can call this as block 1. I can call this as block 2. Such that every time I pass this block that is of 4-bit size, how many extra bits are getting added up? 3 extra bits will get added up onto this block. And this value is always constant. And thereby it's called as linear. So the terminology linear is because of this. Okay. So in this system, it intakes k bits and produces n bit output. So thereby, this linear block codes are usually represented as n comma k, n comma k linear block code. So wherein if I take this as my example, I can also rewrite it as 7 comma 4 because initially we fed 4 bits to this channel encoder, and right after that we got 7 bits as our output. So where 7 is the value for this n and 4 is the value for k. So thereby I can also rewrite it as 7 comma 4 linear block code or LBC. So now it is not mandatory to add. It is not mandatory to add these check bits at the beginning or at the end. So here we have added these check bits here. I can also add the same check bits. I can also add the same check bits at the beginning itself. Again, I'll be considering this message block that is of k bit size. There is no condition that you are supposed to add check bits here itself. It can also be added at the beginning itself. And thereby, this linear block code is also called as systematic code. Thereby, it's also called as systematic coding. Because it doesn't matter if you are trying to add these check bits at the end of this message or at the beginning of this message. We'll be trying to calculate all these check bits based on some algorithm, or there is a mathematical algorithm in order to generate this, and these check bits are getting generated by using a generator polynomial or a matrix called as generator matrix, and it's represented as capital G, and we'll get to know more about this later. Now here we'll first take up a problem. So before we start with the problem, let me tell you this. So again, let's consider our channel encoder. So input to this channel encoder is k bits and output is n bits. And if I consider this block, uh, am I doing any changes onto this k bits? No, it is same as that of whatever I had at my input. So I'm trying to maintain the same k bits as it is, but along with this k bits, I'm trying to add n minus k check bits. Does that I can mathematically rewrite it as I can mathematically rewrite it as I can denote this k message bits as dk. I can represent it as dk, and whatever output that I'm getting, I can represent it as c subscript n. Whatever output that I'm getting, I can represent it as c subscript n. Such that this n number represents the number of bits. So here I had this k input bits, so thereby subscript is k. Now here, the Cn can be mathematically given as C1, C2 till Ck. Then right after Ck plus 1, Ck plus 2 till Cn. This is in turn equal to d1, d2 till dk. And when I multiply this input with something called as generator matrix. So let's see how this generator matrix is given as. This generator matrix has two halves. It has two components in it. Where the very first part of this generator matrix, I'm trying to write this overall generator matrix. So when I multiply this G, when I multiply this dk with that of G, I'll be able to get this ck. That is what I'm trying to depict over here. And this generator matrix will be somewhere in this channel encoder. And in turn, this generator matrix has two halves in it. And this is the demarcation line that I have drawn. This dotted vertical line that I have drawn is the demarcation line, such that the very first half is a identity matrix. Such that it's an identity matrix. And by now, we already know what's an identity matrix. So identity matrix is something that which has all its principal diagonal elements equal to 1 and rest of the elements as 0. Something like this. This is the identity matrix. And this identity matrix is represented as I subscript k. And the other half, that which we have, we call this as parity matrix. We call this as parity matrix. And this parity matrix is given as the first element of this parity matrix P11 followed by P12, and the last element is P1n. Likewise, second row elements are P21, P22, P2n. Likewise, last row elements are pk1, pk2, and the last element of last row is pk pk comma n minus k. So here, this is the size of the parity matrix, or in other words, the identity part is. So this identity matrix is always a symmetric matrix. So its row number should be equal to that of column number. So identity matrix is something whose principal diagonal elements are equal to 1. Excuse me. Okay. So this identity matrix is always a symmetric matrix where its row number should be equal to that of column number, or I can also rewrite it as k cross k. And whereas I also have here this parity matrix, and this parity matrix size is k cross n minus k. Its size is k cross n minus k because your k number represents the number of rows. So this is 1, 2, and the last row number is k. It has k number of rows, and whereas how many such columns? So in order to get to know the number of columns, here we got to, okay, here I had left this, okay. So this is p1 comma n minus k, p2 comma n minus k. Likewise, pk comma n minus k. So its size is k cross n minus k. and we call this overall matrix as generator matrix. So why is this generator matrix in this fashion? It is in this fashion because by now we know that the very first half should resemble what? It should resemble decay. So the very first half should resemble decay, and the next half should resemble this, should be containing the check bits n minus k size. Now here, because the very first half of this Cn from here to here, it should be exactly equal to that of d1, d2 till dk. So thereby, the very first half of this generator matrix is an identity matrix. Whenever I multiply something like d1 into 1 is what? Even though I'm trying to get the C1, but C1 is as good as D1. So whatever I'm having at D1 gets directly reflected back at C1. So thereby, this is what is happening because of this identity matrix. And this happens only till what size? Till CK size. And right after that, from here to here, that is for n minus k bits, when we multiply this message bits with that of this parity matrix, will get this check bits of size n minus k. So parity matrix plays a very important role in deciding our check bits. So we can ultimately represent this scheme as a multiplication scheme between the matrices, such that if I multiply this message matrix D with that of generator matrix, what I'll get? I'll be getting the output as C. And the size of this C is 1 cross n, where 1 represents the row number, and here message is 1 cross k, and the size of the generator matrix is, so what's the size of the generator matrix? So it has k number of rows. So by now we already know that if at all if multiplication has to happen between any two matrix, so the column number of the first matrix should match with the row number of the second matrix. So this generator matrix size is k cross n, because right after multiplication these two gets cancelled out, and we'll be getting 1 from here and n from here, and that is matching the size of our channel encoder output, that is C, and C is always 1 cross n sized. So ultimately we did got to know about this linear block code technique. Is all about, it's all about matrix multiplication. All I got to do is multiply this message matrix D with that of generator matrix G, and this G matrix in turn consists of what all things in it? It contains identity matrix Ik, and along with Ik it also has parity matrix, and this parity matrix is of size k cross n minus k, and the overall size of this G is k cross n. So that's it for now. We will discuss more about this scheme, that is linear block code, in our next class by taking up some examples. We'll try to generate this linear block codes. Or I think we are still left with some time. So what we'll do is we'll take up that problem now itself. We'll take up a very simple problem. In this problem, they have asked us to generate 6,3 linear block code. 6,3 linear block code. And what they have given is just the parity matrix part of generator matrix. They have just given the P part, 101, 0 1 1 1 1 0. So this is the data that I have given, and they are asked us to find all possible code vectors. So back here, what all information do I know? So do I know this size n comma k? Yes, we do know that. So that is equal to 6 comma 3. Meaning, to this channel encoder, I'm trying to transmit 3 bits, and this channel encoder is outputting how many number of bits? 6 bits. Or in other words, how many check bits are getting added up? So check bit size is always n minus k. So if I subtract 6 with 3, so in turn, 6 check 3 check bits are getting added up. 3 check bits are getting added up onto the message. So this is the very first information that I'm able to draw out of this. And the other thing is they have given just the parity part. So by now we know that only when I multiply this D with G, if I multiply this message with G generator matrix, I can get this output code word. But the thing is, I know this G is composed of two matrix. That is, the first one is identity matrix, the other one is the parity matrix. Parity matrix size is k cross n minus k. I know only this part, and this part is what? This is having 3 rows and 3 columns. So this is of size 3 cross 3. Or in fact, I can rewrite it as, I can bring in this parity matrix here itself. But in order to get this generator matrix, what should I be doing? I should also write this identity matrix part. And do I know the value of k here? The value of k is 3. So all I got to do is draw identity matrix. I got to draw an identity matrix of size 3 cross 3 or I3. So this is how I can get my generator matrix. This is my overall generator matrix. And all I got to do is multiply this with this generator matrix with a of input D in order to get C. And let's do that. Now here, they have not given message bits. Message bits are not given. But they are asking us to calculate all possible code words. All possible code vectors or just codes. Now the thing is, do I know the value of k? Yes, we do know the value of k. That is equal to 3. Now the thing is, we are supposed to form a block of 3 bits. There are 3 such places. So how many combinations are possible out here? So 2 power 8, 2 power 3 combinations are possible. So because the value of k is 3, so I'll be writing, I'll do this 2 power 3 such that we'll get 8 combinations. What all 8 combinations we'll get? 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and finally 1 1 1. So because they have not specifically given any message bits, what we'll do is we'll try to write uh, all the possible input messages, and we'll make it to go through this matrix multiplication. We'll try to go through this matrix multiplication. So we know that I can get this C by multiplying input message with that of generator matrix. Now this, what is the size of this input message? It contains 3 bits D1, D2 and D3. And do I know the generator matrix? Yes, we do know the generator matrix, that which has the first half as identity matrix and the second half as the parity matrix. So what was our parity matrix part? It was 101, 011 and 110. Now what I should be doing is I should multiply this with this. Hmm? And in order to do that, let's prepare a table. Let's prepare a table that which contains code name as our first column, and second column is message vector, and the third column is code vector for 6,3 linear block code. So what all message input message combinations are possible? There are 8 possible input combinations. The very first one is 000, 001, 010, 011, 100, 11, sorry, 101, 110, and finally 111. So thereby, because there are 8 input messages, so I'll be having 8 output messages also. C1, C2, C3, C4, C5, C7, and C8. Now all I got to do is take up this starting. So now the thing is, it's quite evident that the very first half of this generator matrix is identity matrix. So thereby, the first half of this linear block code should exactly resemble my message vector. So thereby, all I got to do is repeat the same thing again over here. First write the same thing again, because the first half is identity matrix. You should get same thing. Whatever you multiply it with, you should get the same thing. But only right after that we are having this parity part, and parity part plays an important role in generating our n-k check bits. So let's see how that thing happens. Now obviously, for my very first message, that is 000, I'll be getting here also 000. So let me use other color. Here I'll be getting 000. Now for my next message vector, that is 001, that is for 001, I got to consider only the last row, because here that's how matrix multiplication is done. So for 001, this one represents the last row, So thereby that will I'll be getting over here. And for my next message, that is 010, this one represents the mid row part. So thereby here I'll be getting 011. And for my next message vector, that is 011. So right now I'm having rows. Two rows I got to consider, that which is 011, this, and along with that this, it is 110. And what should I do in between? I should do XOR operation. Just do XOR operation in between. So how exactly an XOR gate works? So this, I can do this XOR, or it's also called as modulo 2 operation. mod 2 addition. I can also call it as mod 2 addition. Such that for similar inputs, I'll be getting 0 as my output, and for different inputs, I'll be getting 1 as my output. So this goes over here, 101. And for this next message vector, that which is 1000, so this 1 represents here the first row, that which is 101. For next 101, for 101, I got to consider what two rows? I got to consider my first row and my last row, because 101 represents that. So wherever I'm having 0, I got to neglect that part. So just consider 101 and 110 and do the XOR operation. Different inputs 1, 1, similar input 0. So this goes over here, 0, 1, 1. And for my next combination, for 110, what two rows am I supposed to consider? I'm supposed to consider these two rows, such that I'll be getting 1, 0, 1, 0, 1, 1. And if I do the XOR operation, what I'll get? 0, 1, 1. So 1, 1, 0 it is here. And finally, I got to consider all the three rows, because all are 1 for my last message vector combination. So here I'll be considering 1, 0, 1, 0, 1, 1, as well as 1, 1, 0. And I got to do this XOR operation. Now here, it's as good as doing modulo 2 addition. So here for 1, 1, so I'll be getting 0. So 0 plus 0 is again 0. Whereas here again it's 0. Here it's again 0. So for the last message vector combination, I'll be getting 0, 0, 0 as my check bits. So this is how we can get all possible code words for 6,3 linear block code. So here you can see that we ended up with 6. So the block size of this channel encoder is what? 6. So this is what we'll be transmitting via, this is what will make it to go through this modulator stage, and right from modulator stage via the channel. And later the same thing will be made to go through this demodulator end. So this is how it works. So this is about linear block code and how we can generate code words from a generator matrix. And this generator matrix will be present where? In the channel encoder part. This will be present in channel encoder. So in this session, we did went through what all concepts. We did went through this error control coding part, wherein we did got to know this is the module where we'll be trying to detect as well as correct errors. And this is something that which happens at the channel encoder part, where if I transmit k bit message, it generates n bit code word, such that the very first half is same as that of my message, but the only thing is we'll try to add n minus k check bits to it. And here we did got to know about the two methods that which are used for controlling errors. One is forward acting error correction, where both error detection and corrections will be done at the receiver end. And this is relatively faster, but the probability of error is higher. And the other method that which we have is error detection, where only error detection will be done at the receiver end. And If any error is caught, it will be discarded, and we will ask we will ask the transmitter to retransmit the correct message. And this scheme is slower compared to that of forward acting error correction, but the probability of error is relatively less. Then we had two types of errors. One is random error and the other one is burst error. Random error happens because of white Gaussian noise, and the sources for this random noises are thermal noise, short noise in the transmitting and the receiving equipment. Whereas burst errors are due to impulsive noise, and this impulsive noise can generate due to lightning, switching transients, and man-made noise. And burst error is something that which affects a group of symbols, not just one, but a group. But whereas random error affects only one symbol. And we did went through types of codes, wherein we did first went through this block codes, and next we went through this convolution codes. And next we specifically went into block codes, wherein that block code scheme is called as linear block code. And back in this linear block code, it is nothing but simple matrix multiplication. This scheme is all about a matrix multiplication, wherein we'll be multiplying input message with a matrix called as generator matrix present in channel encoder. And what's the characteristic of this generator matrix? Generator matrix has two parts. One is identity matrix part, identity matrix part, and the other part is parity matrix. And we did also went through a problem wherein we tried to generate all possible code words for this 6,3 linear block codes. So that's it for now. So if you are having any queries, so please do ask it in the comment section. Or if you are not having any doubts, you can write your name in the chat section. So along with your name, do write your USN. So if you're done entering your name in the chat, so I'll be ending the session. Thank you very much.